Today we are going to discuss an important problem in beam vibrations or even beam stability you can say, which occurs when a beam is subjected to an axial load. So, you find for example, a column. In a column it is subjected to an axial force on the column, and we know that this column cannot withstand any amount of load. There is a limit after which the column will buckle or get destroyed actually. It might get destroyed. This is one kind of axial loading that can happen. There is another kind of axial loading that occurs in case of let us say missiles. So, in case of missiles you have a jet coming out from the rear, and so there is an axial force from the rear on this, but now the property of this axial force is that it will always maintain the angle which is there at the rear end of the missile. So, if the missile is flexible, it is going to, this force is going to maintain the angle. In the case of columns, even if the column deflects, the force for small deflections, the force is still going to be vertical. So, there is a difference in these two axial forces, so which we are going to now discuss. So, when we say beam with axial force, we are going to consider a column like loading. So, let us consider a simply supported Euler-Bernoulli beam with a axial force F. So, we have this an axial force F, and the beam can deflect in this manner. The force retains its direction in this particular case. So, the equation of motion for this beam with the axial force So, these are the two terms for the Euler-Bernoulli beam, and in addition, because of this axial force which is now compressive, we have this additional term. So, in the case of strings for example, the force is tensile. So, this is with a negative sign. So, now it is compressive. So, this is the term because of the axial force. Now, the boundary conditions so the deflection and the bending moment at 0 and L, they must vanish. Now, for this problem, we can use our modal expansion. We know that the eigenfunctions of a simply supported beam is given by sin n pi x over L. So, the solution of of this dynamics with axial force, let us construct that solution as an expansion. In this form. Now, if you substitute this in the equation of motion, and that must be 0. Now, this can be simplified. Now, because of the orthogonality of the eigenfunctions, we can use the orthogonality property to determine these coordinates p j, the dynamics of the modal coordinates p j. So, we multiply this, for example, with sin k pi x over L and integrate over the domain of the beam. So, if you take this inner product, So, you have the dynamics of the modal coordinates given by this equation. Now, suppose we look for solutions of the form c times exponential s t. So, if you substitute in here, so we will obtain solutions of S in terms of this omega k, where omega k is given by this expression. Now, we can make a little bit of simplification here by some redefinition. We can write this where so, using these redefinitions, we can recast this in this non-dimensional form, the eigenfrequency in the non-dimensional form. Now, here there so this S represents the load, the axial force. So, there is a value of this axial force when omega k goes to 0. So, if S is k square pi square, then omega k tilde goes to 0, which means that the system loses stiffness. Now, so this if you now substitute here, so for the lowest mode, so when k is 1, then S is pi square, and from here we know that it is f L square Now, this expression we know as the Euler buckling load. So, this is the Euler buckling load. Now, So, the way we have arrived at this Euler buckling load is through the dynamics. So, let us first see this. So, when we are increasing S from 0, then this omega k is a real number. So, you have solutions in the form exponential. So, when omega k is real, you have solutions So, solutions have this term. So, this times time. So, the temporal variation of these solutions are like this. So, exponential I omega k t. So, which means these are harmonically varying. Now, when this goes to 0, omega k goes to 0, then it loses the temporal nature. So, this is neutral stability. So, you have reached the Euler buckling load for k equal to 1, for example, and the beam has lost its stiffness. Now, if the load is increased further beyond that point, so beyond this value, if you increase the load beyond this value, then omega 1 will become imaginary. So, let us say it becomes I alpha for f greater than for f greater than this buckling load, omega 1 becomes imaginary. In that case, so you have the solution as an exponentially increasing and exponentially decaying terms. Now, at a finite time, the exponentially increasing solution is going to dominate. So, even for a very small disturbance, initial disturbance, so the solution is going to have this nature. This is known as divergence instability. So, this kind of behavior is known as divergence instability. So, when the axial load exceeds the Euler buckling load for the first mode, then you have this divergence instability and the beam actually buckles. So, let us look at the variation of this frequency with increasing load. So, here I have plotted this non-dimensional frequency, circular frequency with the non-dimensional load. So, when the load is 0, you have this is the first circular natural frequency non-dimensional, and as the load increases, this falls, and here at a certain load it goes to 0, the circular natural frequency goes to 0. So, this is the buckling load or the critical load. Now, let us look at this picture in the root locus diagram. So, S is the coefficient of the in the exponential term in the solution. So, here I have plotted the real part of S and the imaginary part of S. So, S is plus or minus I omega. So, plus I omega tilde and this is minus I omega tilde when the load is less than the critical load or the buckling load. As you increase the load, these roots they go to 0. Once they reach 0, then they move on this axis. So, here as we have seen, so we have this plus minus alpha. Now, there is this root on the positive side which is going to lead to instability. So, that is what we look here in the solution. So, we have an exponentially increasing solution and which looks like this. Even with a very small disturbance, it is going to exponentially diverge. So, this is the divergence instability. So, a beam with axial force will show divergence instability if the force exceeds the Euler buckling load. Now, this can be used to estimate the buckling load of a column without destroying the column. If you want to estimate the buckling load of a certain column, so if you give this axial load and keep increasing it, and when it reaches the buckling load, this column is going to deflect, have large deflections, and very likely this column is going to get destroyed or spoiled. You cannot use it. But suppose if you want to have devise a procedure of non-destructive evaluation of the buckling load of a column experimentally. So, you can use this dynamic feature. Now, you increase the load and look at the lowest eigen frequency, and when it reduces and comes to a very small value which you can tolerate, you can estimate from there on, use the expression of the variation of the eigen frequency with the axial load to finally find out the intersection without actually doing the experiment, without actually destroying the column. So, you extrapolate the curve that I have just shown you with load versus the natural frequency. So, you extrapolate the curve and you obtain the intersection with the x axis, which is going to give you the buckling load without spoiling the column. Next, let us look at this example of a beam with a follower force. Now, what is this follower force? So, let us consider a cantilever beam. With a force at the free end. This is an axial force once again. But then this force has this property that when the beam deflects, so this is an exaggerated figure. So, when the beam deflects, the force is going to maintain the same angle as the center line of. So, it is always going to be tangent to the center line or the neutral fiber of the beam at the free end. Such a force is known as a follower force. So, it follows the tangent to the neutral fiber or the center line of the beam. Now, we need to so such examples are observed in missiles. So, this kind of dynamics is observed in missiles, inflexible missiles, so to say, then also in fluid carrying jets. So, when you have a pipe or a tube which is which has a jet at this end. So, the water comes out and that gives force on the free end of this pipe, and that is also a follower force. So, these are some examples. Now, we need to derive the equation of motion of this system. One thing you can immediately see that this force has a transverse component which is given by this is of course assuming that this is small. So, if you make this assumption, then the transverse component of this force at x equal to L may be written in this form. Now, this force is a non-potential force, which means that this does not have this cannot be derived from a potential. It is not a gradient of any potential. So, to derive the equation of this system, if you want to use the variational principle to derive this equation, which is a safer way for this system, because the dynamics is a little tricky, as we will very soon see. So, let us so since we have a non-potential force, we have to use the extended Hamilton's principle. To derive the equation of motion for this system. So, in extended Hamilton's principle, what it says is this must be 0. Now, here this is the virtual work done by non-potential forces. So, in our case we have this as the non-potential force, and we must include the virtual work done by this force. Now, the Lagrangian, let us first write down the Lagrangian. So, this is 1/2. So, we have the kinetic minus potential energies. So, that comes from the kinetic energy of a beam element minus the potential energy due to flexure and then there is a potential energy because of this axial force. So, because of axial straining. Here I have taken the sign of this F appropriately, so that this indicates a compressive force. So, if F here is positive, then it is a compressive force. Now, so this is the Lagrangian of the full the beam. Now, the virtual work done by this non-potential force so it's given by this. So, that turns out to be So, you have to note that this virtual work is done at the point x equal to L. So, now we put these things back in our extended Hamilton's principle. So, if you do that, so we have so let me write out the variation directly. So, that is extended Hamilton's principle. So, we note that this virtual work already gives a boundary term in this equation. So, now we integrate by parts this term with respect to time, and if you use the arguments of variational calculus or the so at T1 and T2 the variation must vanish. So, I am not going to write the term the boundary term generated because of from this term at T1 T2. Then this has to be integrated by parts with respect to space, and similarly this. So, if you carry that out, so once when you integrate by parts this term 2 times. So, this is one term, this is the other term with delta w, and this term also gives you delta w and then we have this already as the boundary term, and then we have the integrand in this So, delta w taken out and that must vanish. Now, using the standard arguments that the variation over the domain and over the boundary must vanish independently. So, we can easily see that from here we obtain the equation of motion and then the boundary conditions, considering that the beam is a cantilever beam, and here if you look at these two terms, now here, so this term and so this term evaluated at L and this term is going to cancel, and finally, what you are left with at x equal to L so the natural boundary conditions at x equal to L So, at x equal to 0 this is going to vanish, at x equal to L this must be 0 and the other term is comes from here, which is the moment, the bending moment. So, one term at x equal to L comes from here, the other term comes from here. This term gets cancelled at x equal to L. So, this is the equation of motion and the boundary conditions for the beam, for the cantilever beam with a follower force F. Now, it is interesting to note here, you see the first of all the equation of motion is same as that with the that of the beam with a normal axial load. The other thing is there is this boundary conditions are all homogeneous. Now, that is very surprising because there was a transverse force in, at this free end of the cantilever, which is this, but then this term cancels the boundary contribution from the from this dynamics. So, finally, all the boundary conditions are homogeneous, and this is a very surprising thing in the case of the follower force, beam with the follower force. So, let us now look at the eigenvalue problem. So, we look for a separable solution, the complex solution of the form, let us say w x exponential s t. Now, when we substitute this in the equation of motion and we do the simplifications, so that is the differential equation for the eigenvalue problem, and along with this we have so this describes the eigenvalue problem. Now, let us make some redefinitions here. So, first we search for a solution of this W suppose we look for solutions of W in this form, then substituting here we obtain now we can write this as where we have used these definitions. So, using these definitions we restructure our characteristic equation in this form. So, here we are going to solve for beta. So, we can see that there will be two solutions of beta. So, this is one solution of beta. The second solution reads So, I have written this beta 1 and beta 2 in such a way that I can write my solution of W as so that is the solution for W, general solution. Now, we must use the boundary conditions. So, the boundary conditions as I had written down So, the slope, so displacement slopes being 0. So, this So, this implies and the fourth condition So, these are the boundary conditions. Now, so they can be recast as a matrix A times this is 0. So, for non-trivial solutions of these coefficients, the determinant of A, and remember this A, that A is a function of omega tilde and S, the loading, this must vanish. So, if you so you can solve for a given load S, you can solve for the circular natural frequencies of the beam, and this can be solved numerically. So, here this shows the results of such a solution. So, when the load is 0, the first two circular natural frequencies non-dimensional are these 2 points, and as the load is increased, as you can see that omega 2 decreases while omega 1 increases, and they coalesce at a certain value of load. Now, this is the value which is critical, because after this they vanish. Now, to see what happens to these eigen circular eigen frequencies, we look at the root locus, which again we plot S, the real part and the imaginary part of S. So, so remember that S is plus or minus I omega tilde. So, when you have the load less than the follower force magnitude less than the critical value, then these are the this is a distribution of the circular natural frequencies, plus or minus I omega 1 and plus and minus I omega 2. Now, as the load is increased, these two come together and coalesce at a certain value, which is the critical value of the load, and then they move into the they have real parts as well. So, this branch where this root has a positive real part, similarly this root has a positive real part. Now, therefore, you have solutions so these were the solutions. Now, if omega becomes as you have seen in the root locus, you have both plus minus alpha plus minus I beta. So, if you have if you consider this solution, then you have solutions like this. So, you have exponential term along with a fluctuating component. So, which means the solution will look like so this has an exponentially increasing envelope, and so this is T versus the displacement. This kind of behavior is known as flutter. And we observe flutter instability in beams with follower force. So, there is an exponentially there is a fluctuation with exponentially varying amplitude. So, to summarize what we have discussed today, we have looked at the dynamics of beams with normal axial force and follower force. So, with that we conclude this lecture.